Okay, so this group has 8 elements. And we know what these elements are. When we talk of this group mode 8, we mean the elements 0, 1, 2, 3, 4, 5, 6. These are the elements in this group, and there are 8 of them. No, 7. There's a 7 here. So it is, when we talk of Zn, then we are talking of elements 0 up to n minus 1. So in this case, our n was 8. So 8 minus 1 would be 7. Now that is about the group. And we also talked of multiplicative group, which we denote by, we put a star here. So that means without a 0. And of course, when we talk of a multiplicative group, this would be a group of elements which are relatively prime to 8. And we know what that means. And so these elements which are relatively prime to 8, and that means an element is relatively prime to 8 if that element and 8, the GCD is 1, or the only common factor is 1. The only common factor, for instance, 1, 3, 5, and 7. So these are the elements in this group, Z star 8. Elements which are relatively prime to 8 are 1, 3, 5, and 7. So the order of this group, therefore, is the number of elements here, 1, 2, 3, 4. And we had looked at this earlier. So today we want to look at the order of the element in the group. So for instance, this group here, Z8, has various elements here, this element, 1, 2, and so on. So our interest is to find out what is the order of each of these elements in the group. So that is our interest. So again, we will define what we mean by the order of an element. It's different from the order of a group. That is why I began by looking at what we did about groups. So that when we talk of the order of a group and then talk of order of an element, you don't confuse the two. The order of an element, we are talking about the element of a group. What is the order of that element? So that order of an element is slightly different from the order of a group, because the order of a group, we talk about the number of elements in the group. But now when we talk of the order of an element, unless the definition I've given here is where the group is multiplicative. When the group is multiplicative, like the one we've seen, this group has elements 1, 3, the elements which are relatively prime, 5, and 7. So the question is, what is the order of 3, for instance? What's the order of 3? That is the question. That's the question we are answering today. Or what is the order of 1? Or what is the order of 5? And we denote it that way. Or what is the order of 7? So that's what we are looking at. Now, so if you're given an element R in the group, when we talk of the order of that element, if the group is multiplicative, then we mean the smallest integer, which when raised to R, gives you the identity element. For multiplication, this is what it means. We mean what is the smallest element or integer when raised to R would give you 1, where 1 is the identity element under multiplication. So that is the definition of the order of an element. Now, so that is about multiplicative group. That is what I wrote, and I said the order of an element G in G, where G is the group, and this is the element, is the smallest integer, positive integer, which when raised to G gives you the identity element. And that is, if that order exists, some cases, the order will not exist. In other words, in some cases, you will not be able to find an element which, when raised to G, gives you E in some cases. That's why I said, if such N exists. Now, if it doesn't exist, then we say that the order of that element is infinite. If it doesn't exist, we say that it's infinite. We say it's of infinite order. So then we can denote its order as this way, using infinity, using this symbol, if we cannot get that element. That is under if the group is multiplicative. What about if the group is additive? How do we get the order of the element? And I'll be showing you examples just in a few minutes. Then we look at how to do that using our code. Now, if the group is additive, for instance, I'm talking about this group, which is an additive group. You can see there's no star. So this has elements 0, 1, 2, 3, all the way up to 7. All the way up to 7. These are the elements there. So you're asking, what is the order of 0, for instance? What's the order of 1, for instance? What's the order of 2? What's the order of 3, and so on, up to what's the order of 7? So that is a question. Now, so what we mean by that, if we have an element A in the additive group, an element A of this additive group, and we are asking about the order of that element, then we are talking about the smallest integer n. We are asking ourselves, what is the smallest integer n, which when multiplied by A gives you the identity element. But the identity element under multiplication is 0. So we are asking ourselves, what is that smallest element when multiplied by A gives you 0? So that is what it means. And that's what I've given here as the definition. I've said that if I began from here, said if the binary operation on G is addition, then the notation becomes this. Instead of what we had earlier was G raised to that. If the group is multiplicative, but now when the group is additive, it's just N times G. It's N times G, not G raised to N. So then you're asking ourselves, what's the order of G? So the order of G would be this N. If at all, N times G will give you 0 under addition. So that's the definition of the order of an element. So I just want us to then look at examples so that we understand what it means. And then when we look at examples, we'll be able now to see how to write the code using that same example. Just the same way we'll be doing the example, that is the same way we'll write the code to give us the order of elements of a group. Now, the first example is here. I'm given an additive group, Z7, and of course, I've added here, there's a plus. It's not necessary because anybody seeing this, this person should know that this is a group under addition. Anybody seeing this, but I've just added addition for the sake of anybody who may not be aware that I mean that this is a group under addition. Of course, this is how you denote it. This is how you write a group. You can write it this way to mean there's a group under addition, or you can write it this way. Now, if it's not a group mod n, then suppose it's just G. G, you see, this one you can easily tell is an additive group. But if somebody had just given G like that, without telling you, without G, you see, this one does not have mod 7. So this person is supposed to tell us that it's a group under addition. So you add that so that you are specific. You are telling us it's a group under addition because there's nothing to show that it's a group under addition if you don't add the plus sign. And if it's a group under multiplication again, and there's nothing to show, then you must add multiplication. Or if you don't want multiplication, then you can add this dot, which also means multiplication. And you mean that this is a group under multiplication, This is a group under multiplication, this is a group under addition. And when you're talking about integers, integers mod n, then you don't need to add even plus or minus or multiplication, because the number here will tell. No, if it doesn't have a star, you can tell that it is a group under addition. But if it has a star, then you can tell it's a group under multiplication, if it has a star. But now the question is, what is the order of 5 in this additive group? What's the order of 5? So the question is, from our definition, the question is, which element, when multiplied by 5, gives you 0? Which element, when multiplied by 5, gives you 0? So you just begin. Of course, you know what Z7 is. Z7 has element 0, 1, 2, 3, 4, 5, 6. We are doing up to n minus 1. So the question is, what element, when multiplied by 5, out of these elements, which one? Out of these elements, not necessarily out of these elements, when it's a multiplicative group, but the elements you are considering must be less than 7. The elements you are considering, there must be less than 7. Now, so we just check to see which one, when multiplied by 5, gives you 0. No, you check from here. Check from here, from 1, not from 0. Check L1, 2, 3, and so on. But that is why I said not necessarily these elements, because what we are doing is in a real sense, under addition, what we are doing under addition, and that is how we'll be writing the code. We want to add 5 to itself. That's what I mean. We want to add 5 to itself until the result is 0. We want to add 5 to itself until the result is 0. So 5 once is just 5. 5 twice, this mod 7 is 3. 5 plus 5 is 3. Mod 7. Is that okay? And then what about 5 plus 5 plus 5? This will be 1. Mod 7. And we know what we are doing because we've done this before. What we are saying is, when you talk of mod 7, you are saying the result that you get, the result here will have been 10. But now this 10 you're dividing by 7 and writing the remainder. You're writing the remainder. So 7 will go there once and the remainder will be 3, and that's what I write. That is how we do modulus arithmetic. That's what we've been doing. So again, we are saying 5 3 times will be 5 plus 5 plus 5, which is of course 15. But now this 15 divided by 7, what is the remainder? That's what I've written. That's what I've written there. So the 5 plus 5 plus 5 will then be 1. And of course, you only needed to do this because we already know 5 plus 5 is 3. So that means this part is 3. 5 plus 5 is 3. So 3 plus 5 then becomes 8. But because this part is 3, 3 plus 5 then becomes 8. But now 8 is more than 7. Since 8 is more than 7, you divide it by 7 and write the remainder, and of course you get 1. 8 divided by 7. Now, so 5 3 times has given us that. What about 5 4 times? 5 4 times. 1, 2, 3, 4. 5 3, we know it's 1. So up to here it's 1. Then 1 plus this will be 6. Will be 6. Of course, you can just add. This will be 20. Divided by 7, the remainder will be 6. What about 5 times? 1, 2, 3, 4, 5. This will be 6 plus 5, which is 11. Divided by 7, the remainder is 4. So the answer there is 4. Yes, because that would be Yes, that will be 4. Or of course, you can just add 5. These are 5 times, which is 25. Divided by 7, we'll get 21. The remainder is 4. What about 5 6 times? 5 6 times. So 5 6 times will be 5 plus 5 plus 5 plus 5. These are 1, 2, 3, 4, 5. Then 6. 1, 2, 3, 4, 5, 6. We are doing it mod 7. So this will be 2. Because 1, 2, 3, 4, 5. 5 of them is 4. 1, 2, 3, 4. 1, 2, 3, 4, 5. This 5 gives us 4. Then plus this 5, that is 9 mod 7, that is 2. 1, 2, 3, 4, 5, 6. What about 5 7 times? 1, 2, 3, 4, 5, 6, 7. This will be 0. This will be 0. So for those who don't know, we just added, these are 5 7 times, that is 35. 35 divided by 7, it goes there 5 times, but we are interested with the remainder. So the remainder is 0. So instead of doing what we've just been doing, but of course, this is how we shall write the code. This is how we shall write the code. But of course, according to my definition, instead of doing this, 5 ones is just like 5 times 1. So this would be, instead of 5 plus 5 will just be 2 times 5. So that means 5 2 times. 5 2 times is 3. Then this would be 5 3 times. 5 3 times. So you're asking yourself, what is the smallest number when multiplied by 5 gives you 0? And we found it to be 5 7 times. 5 7 times will give you 0. 5 7 times. 1, 2, 3, 4, 5, 6, 7. 5 7 times. So that is what we do. But of course, I try to, my definition says you just multiply by 1, then multiply by 2, multiply by 3, until you get that integer. When multiplied by 5 gives you 0, and when you proceed like that, you find that 5 times 7 is 0, which means that the order of 5 is 7. The order of 5 is 7. I can take another example just to emphasize that, so that this time I'll not be adding, I'll just be multiplying, because I know when I add 5 2 times, the same as 2 times 5. That's what I want you to understand. When I add 5 3 times, the same as 5 times 3. That's what I want you to understand, so that we can move fast. So that 5 ones is just 5 times 1. Now that is if the group is additive, and that is how you get the order of an element in that group. So we've just considered this group has several elements, but we've considered 5. Just wanted to find what the order of 5 was. Now there's another additive group here, and the question is, what's the order of 6 and what's the order of 3? So the question is, find the order of 6 and then find the order of 3. So we want to find an element which, when multiplied by 6, gives you 0. So we just begin by trying. We just try. 1 times 6, we get 6. 2 times 6 gives us 2, because it's 12, but 12 divided by 10, the remainder is 2. That's how we do that, because this is modular arithmetic. And then this 3 times 6 would be 18, which is 8. And then we want to, until we get 0, 4 times 6 would be 24. Divided by 10, the remainder is 4. 5 times 6 is 30. Divided by 10, the remainder is 0. So 5 times 6 gives us 0. In other words, the order of 6 is 5. The order of 6 is 5. Now, so we want to try another element, and that is 3. Want to find the order of 3. And to find the order of 3. So again, we are looking for an element which, when multiplied by 3, gives us 0. So 1 times 3 is 3. 2 times 3 is 6. 3 times 3 is 9. 4 times 3 is 2. 5 times 3 is 5. 6 times 3 is 8. 7 times 3 is 1. 8 times 3 is 4. 9 times 3 is 7. And then 10 times 3 is 0. If there is anywhere you don't get, you just ask. Of course, just doing modular arithmetic. We are doing modular arithmetic here. And therefore, the order of 3 is 10. The order of 3 is 10. That's how we do it. If the group is additive, I want to look at if the group is multiplicative. But before that, there's something I want to just emphasize here. Look at 6 and 10. Look at 6 and 10. And then look at 3 and 10. 3 and 10, the GCD of these two, or the only common factor is 1. The only common factor is 1. So we say that 3 and 10 are relatively prime. Relatively prime. Now, so if the number that we're looking for, the number whose order we are looking for, is relatively prime to n here, then we expect that the order of this number will be n. The order of this number will be n. That is why when 3 is relatively prime to 10, we discover that the order of 3 is 10. The order of 3 is 10. But this other one is, they're not relatively prime. 6 and 10 are not relatively prime. And so since they're not relatively prime, we discover that the order is not equal to 10. But look at this. The other way of doing it, the order of the group is 10. The order of this group is 10. And then 6 and 10, the GCD of 6 and 10 is 2. Is 2. So when you take 10 divided by 2, therefore, you get 5. And that is the order we got. That's the order we got. This is the easiest way of doing it. But my code, I've used this method to do it. You can also at your own time try and see whether you can do it this way. And this method will only work for an additive group. For an additive group. Let me just again explain so that as you write the code, you can also see how to write. You can also see how to write, because I'm seeing this could be easier. This could be easier also to write the code, so that you just tell the code. Of course, the code it must know what the order of the group is. So the order of the group divided by the GCD of order of group, GCD of order of group, and element. And element we are looking for. The element we are looking for. So let me again show you. Even using 3, let me show you using 3, this 3 here. The order of this group is 10. The order of this group is 10. So the order of the group is 10. Then the GCD of 10 and 3 is 1. The GCD of 10 and 3 is 1. So that means 10 over 1, which is 10. That's how you can also find it. And of course, if I go back and do the previous example, using that same method, so that as you write the code, you can also look at how to do it that way. So the order of this group is 7, and the GCD of 7 and 5 is 1. So that is 7 over 1, which is 7. So that means the order of 5 is therefore 7. That is what you got. That is what you got. That is if the group is additive. Now, there's something I've said here. From the above examples, notice that if the element A is relatively prime to n, I didn't complete the statement. What is it? Notice that the order of A, the order of A will be n. The order of A will be n if A is relatively prime to n. That is something I just wanted to emphasize. But of course, I've shown you the other way of doing it. We're using the order of the group over the GCD of the element and the order of the group. Now, when the group is multiplicative, like this one, the group is multiplicative. We know the elements which are here. We know the elements in this group. This is a group that is multiplicative. We know that the elements here are 1. Those which are elements which the only common factor between them and 10 is 1. So 1 is one of them, 2 is not, 3 is another one, 4 is not, 5 is not, 6 is not, 7 is another one, 8 is not, 9 is another one. So these are the elements. But the question I've asked is, what is the order of 9? What's the order of 7? So by definition, we've said under multiplication, if the group is a multiplicative group, the order of A will be the element n, such that A raised to n gives you identity element, gives you the multiplicative identity element. So that is how it is. So therefore, that means we want to get the order of 9. And so we want to raise 9 to 1, raise it to 2, raise it to 3, raise it to 4, up to raise it to 9 itself, until we find an element that will give us identity 1. So when you raise 9 to itself, what you get is 9. When you raise 9 to 2, what you get is 1. So that means, therefore, the element which, when raised to 9, gives you identity is 2. So 2, therefore, is the order of 9. So how did we get 1 here? How did we get 1? Let me again explain. We are doing it mod 10. So 9 times 9 will be 81. So when you divide 81 by 10, the remainder is 1. So that's how we get that. Okay, let me do this. Let me do this again. 7. 7 raised to 1 will be 7. 7 raised to 2 will be 49. 49 mod 10, the remainder is 9. And then 7 raised to 3. Of course, 7 raised to 3, we know it. We know it's the same as 7 raised to 2 times 7. 7 raised to 3 is just 7 raised to 2 times 7. And 7 raised to 2 is 9. Then times 7, that will be 63. Mod 10, the remainder is 3. The remainder is 3. What about 7 raised to 4? 7 raised to 4, of course, we know this. We know that it's 7 raised to 3 times 7. But 7 raised to 3 is 3. Then times 7, that gives us 1. If you want, you can just use your calculator and do it 4 times. And then divide by 10, you see get 1. So therefore, the smallest element, which when raised to 7, gives you 1, is 4. So that is the order of 7. That is the order of 7. But this is not how I wrote the code. How I wrote the code, I just understood what this one means. This is how I wrote the code. I took 9 times itself, 9 ones is that. Then this, instead of writing 9 square, I understood it as 9 times 9. I understood it as 9 times 9. So that gives me 1. So again, for this one, I understood this as 7. Then this will be 7 times 7, which is 7 square, because that is 9. Then 7 times 7 times 7, that will be 3. And then 7 times 7 times 7 times 7, this will be 1. That will be 1. So that's how I wrote the code. Now, so we've just been finding for instance, this question just wants us to find the order of 9 and the order of 7. Someone else will ask for the order of the other elements or the order of all the elements, and it's important for you to get. These orders are very important, of course, when we're looking at primitive roots, which are very much applicable in cryptography. And that is when we require these orders, when we're talking about primitive roots. So they're very important to us at that time. Oh, the formula I was talking about for the additive group is also here. So at your own time, you can look at it. Okay, let's look at this other question, then we go to the code. From the way this one is, this is an additive group. Because it has no star here, there's no star, so it's an additive group. So of course, we know how to get the order of an element. We have those 2 ways. So I've decided to use this other way where I say the order of the group is 10, and then the GCD of the group and the element is 2. So when I divide, I get 5. Now let's now go straight to the code and see how the code will be giving us the orders. Okay, this is my code. And this is the one I want to use to get the order of additive groups. I want to find out whether you can see it. Are you able to see this code?
Yes.
Okay, thank you. Now, this code, I've placed my element 8 here. This is my main function. This is my main function, and the main function, of course, I've written the code using big units. That means I can find even for bigger elements. You will have used U32 or U8, depending on what you want to deal with. So, but I want to use 8, just 8, because it's supposed to give me the order of every element. So there'll be so many. So that is why I want to just use a smaller number. Okay, so let me just run this code and I see what it gives me. I'll go run. So the code has run. You can see the result at the bottom.
Yes.
Saying the order of 0 in Z8 is 1. The order of, that means you can add 0 once, just to add it once to get 0. That's what it means. The order of 0 is 1. And then the order of 1 is in Z8 is 8. That means you'll add 1 8 times to get 0. Then the order of the other elements are this given. Just want to change the element a bit, and let me increase it a bit. because it's printing so many things, so that although you can deal with the very large integers, but I don't want, because it will take long to print all of them. Let's find out. So I've told you to print, I've told you to say order of in Z, this is that. So it gives me the result there. Let me see what this one gives me. Okay. So it has given me the order of every element up to 15, because this group has up to 15, as elements up to 15. It's saying the order of 15 is 16 itself. Of course, you can see that 15 and 16 are relatively prime. 15 and 16 are relatively prime. So you expect that the order of any number which is relatively prime to 16 will be 16. For instance, 13 is relatively prime to 16. So you expect the order of 13 to be 16. And 12 is not relatively prime. What we expect is that the order of 12 will be 16 divided by the GCD of 12 and 16. The GCD of 12 and 16 is 4. So 4 divided into 16 will be 4. That's what it has given us. 11 is relatively prime, so the order should be 16. 10 and 16, the GCD is 2. The GCD is 2, and therefore 2 divided into 16 should give us the order, which is 8. So I just want to explain how this code works. Of course, I've said I've used big unit just to ensure that I'm dealing with big numbers. Let me try one big number and see what I get. Let me just add that. Not very big, just slightly big. And of course, it has so many elements. We have elements from 0 up to 16,081. Those are very many elements. Let's see how long it will take to do that. It's finding the order of every element. Once it's done, it stops. It still has a long way to go because it's now in 2000 and it's supposed to go up to 16,000. I think I should just leave it to run as we continue with other things, huh? Because it's now doing 2,600 and something when it's supposed to go up to 16,000. So that's why I said if you give it a big number, it will still run, but now it will take time because it's, and it's going through all the steps that I was showing. It's going through all the steps. So for instance, take 1 multiplied by itself, then take 2 multiplied by 1, take 2 multiplied by 2, and so on until you find what the order of 2 is. Then go to 3. Take 3 multiplied by 1, 3 multiplied by 2, 3 multiplied by 4, 3 multiplied by 5. So going through all those steps until it finds the order of 3. So you can see it's the steps are, there are so many numbers to try. So it's trying all those numbers until it prints what the order of the element is. So let it continue as I explain how the code works. So the code is here. So I have this library. This library, the big unit, is just to ensure that this code is able to handle big numbers. And then you have the trait, the num trait, that ensures that This code can handle 0 and 1, and of course, convert them to big units, and so on. So I have two functions. I have this function for finding the order, and then I have the main function. So this is where everything is happening. Yeah, this is where everything is happening. I will input N and R. Of course, R is the element whose order I want to find. R is the element whose order I want to find, and then N is the mode. N is the mode, and then big units, also big units. So just to ensure that they are converted to big units. Of course, in my example, N is 8. N is 8 in my example. The one I began with, N is 8. So this is our that is our mode. Now, A here is to stand for all the elements between 0 and 7. So I want this code to be able to give me the order of 0, the order of 1, the order of 2, all the way up to the order of N minus 1. The order of N minus. So all these, I've called them A. I've called all those A. So that is what A means here. A means N of these. So of course, it will be considering N and 0, and then finds the order of 0. And then it goes ahead and considers N and 1 when A becomes 1. And that is why I've said that A is supposed to be mutable. A is supposed to be mutable. Because you can see A at one point be 0, at another point be 1, at another point be 2, and so on up to N minus 1. So because I want, now, but you can write a code that just gives you the order of a specific number, where you just input the N and the A, and then it gives you the order of A. But for me, I wanted it to give me the order of all elements of that group. Now, so what is happening here? What is happening here? What is happening here is that, of course, you begin from this part, the main function. The main function, you put your mode, and then it will be calculating for A in the range 0 to N. But what Rust, when you write, and Rust understands this as when you write 0 to N, Rust will understand that as 0, 1, 2, 3, all the way up to N minus 1. You'll understand it that way. Now, so this is, these elements are youth at 2, but then this A will be converted from youth at 2 to big unit, converted to big unit. And then the N also will be converted to big unit. Now, so what this main function does is that it will call the find order function, so that find order function finds the order of N and A. So for instance, we've said that A, in our example, we've said that A is 0, 1, 2, up to 7. So when A is 0, this function will call for the find order function to find the order of N with 0. So this one then does that work. And then once it's done with that, the main function calls for the next one, because it requires, again, the order of 1. So it will call for this find order function and give it N and 1. N and 1. Then this one will be doing that, gets the order of 1. Then proceeds again. This one will then make another call for the order of when A is 2 and N is still 8. and then this one does it. So this one has, after this one is complete, after this one has done all of them, this one will then print the results. So what I just want to explain then is how does the find order function work? But we've seen what the main function will be doing. The main function will be calling, and then the find order function works and finds the order. Now, so under the find order function, the function knows that we want to find us a constant k such that k times a should give us 0. That is all the function knows. So this function then begins by letting k to be mutable, but initially takes it to be 1. Initially make it 1, make k to be 1, but it will be mutable, which means it will be changing. It will be changing. So it's 1 at another point, go to 2, and so on. Then let the sum also be mutable. So initially, the sum, we let it to be a. So you know what the code understands? The code understands that if you have a, you will take a plus a, you will take a plus a plus a, that's what it's saying. Then you take a plus a plus a plus a, and so on. So it's beginning by saying, and this one is the same as a k a. This one is the same as, so k here is 1. K here is 1. So in fact, k here is 1. So in this case, k is 2. In this case, k will be 3, and so on. So k is mutable. So it begins by saying, let k be 1, and let the sum be 1. And they are mutable, they'll be changing. Then we begin with this loop, the while loop. The while loop. And the while loop says, if the sum divided by n does not give a remainder equal to 0. Let me just read it the way it is. While the sum divided by n, while the sum, I think if I read that way, it becomes easier to understand. While the sum divided by n is not equal, that means the remainder of dividing the sum and n is not, this means not equal, is not equal to 0. Let me show you, for instance. For instance, let me talk of 8 as our n, and talk of k, no, a as 3. So we've just made k to be 1. And our sum, initially, our sum is 3. Our sum is 3 initially, because we said initially the sum would be a. So what this one is saying is that while the sum divided by n does not give you a remainder of 0, you proceed and come here. You proceed and come here. So what is it in our case? In our case, the sum is 3, and our n is 8. So when you take 3 divided by 8, this is not equal. Is not equal to 0. Is not equal to 0. This is how Rust writes it. In fact, in mathematics, we will have just written that. So this is not equal to 0 because 3 divided by 8, the remainder is not 0. The remainder is 3. The remainder is 3. So if that is the case, so that means this loop continues. This loop will continue until the remainder of dividing this sum divided by n, until the remainder will be 0. So while the loop while the remainder is not 0, the loop continues. So that process, the process inside the loop continues. While the remainder is not 0, the process inside the loop continues. So what is it inside the loop? What does the code say? If the remainder is not 0, our k was 1. Our k was 1. So if the remainder is not 0, make k 2. Increment, this is what it has written. K, increment k by 1. Increment k by 1. Increment k by 1. So k becomes 2. K becomes 2. What about the sum? The new sum now becomes the old sum plus A. The old sum plus A. Let me show by an example so that we understand the code. Just a small example here. I want us to understand what the code is saying. I want to use 3 and 8. I want to use 3 and 8. No. Let me use 6. Let me use 6 and 8. Because 3 and 8, I'll go up to 8 times. My A is 6. My N is 8. Now, let's begin from here. We let K be 1. We let K be 1. And then again, let the sum be A. Now, let's try. Let's now come here and test. Let's test a 6 on division by 8. And want to see if the remainder is 0. But this remainder is not 0. This remainder is not 0. Since the remainder is not 0, we come inside here, inside the loop. What does it say? We now say, let K be 2. Increment K by 1. Increment K by 1. So K now becomes 2. What about our new sum? Our new sum now, let the sum now becomes the sum we had plus A. Our A is 6. So our sum is now 12. Our sum is now 12. Now, since the sum is now 12, we test this again. We test this again. Sum, which is 12, on division by 8, our N, the remainder is what? The remainder is not equal to 0. The remainder is not equal to 0. Because the remainder here will be 4. So it's not equal to 0. So it's not, if it's not equal to 0, again, we repeat the same process, increment K. So our K, we increment K by 1. So K now becomes 3. And the sum now becomes the sum we had, which is 12. Then add 6. This will be 18. Then again, try this part. Try this part. And the part is sum on division by N should not be equal to 0. Now, if it's not equal to 0, we proceed. But if it's equal to 0, we stop. So this will be 18 on division by N, which is that the remainder is not equal to 0. Because this is the remainder will be 2. And because of that, we increment K to 4 now. it was 3. We now increment it to 4 and also increment the sum to the sum that we had, which is 18. 18 plus 18 plus 18 plus what? Plus our A is 6, which will be 24. And then again, try sum divided by n, which is 24, divided by 8. The sum this time, is it 0? And the remainder. If 8 goes there, into 24, the remainder is 0. So since the remainder is 0, we exit the loop. Exit the loop, and when you exit the loop, K becomes the order. K becomes the order. So that means our K is 4. So therefore, the order of 6 is there for 4. The order of 6 is there for 4. So that is how it's doing it. That's how it's doing it. Now, once it's done with the 6, the main function asks another element. We'll then ask for 7. And then ask for the order of 7. And again, this find order function goes through the same process and gives it the order of 7. Now, this one is just keeping. Once it's given the order of 6, it stores it here. This is where it's stored. It's stored as a vector. Where is that? No, it's not storing somewhere. Okay. Now, but what this one is doing is that it asks for 0, it asks for 1, it asks for 2, it asks for 3, all the way up to n minus 1, and it's just calling for it here. Where is that? Find order here. And then when it asks for 1, this one does, using the steps I've explained. Once it's done, this one asks for 2. And then again, it gives the result, and so on and so on. And the process continues. Now, so the one that was running has now completed. Let me just show you. It has now run to completion. It now has the results down here. Down here, it has all the results, all of them. Because it's just showing this few because of the space. So what we saw is that once the main function asks, this one does, and once it does, this one displays that order, and then it asks for another one. This one does, and then once it does, this one prints that order, and so on. So there's no storing, of course, it's just printing and printing and printing. And that's what we saw. It was, when we left, it was still printing. Every time the result comes in, it prints it. That's what we saw last time. Now, so the explanation I've just given, it's here. You can look at it later. Of course, I've given them why we're using the library, big unit, and this other one, I've given the reason. And then the find order function is here, the find order function. And then from there, I explain how the find order function works. There is n, it inputs n, and then it inputs a. So in the find order function, there is n and there is a, which are then converted to big units. So I've said it then makes the initial k to be 1. And then the sum is also initialized to a. Just make it initial value, the sum to be a. And then while the loop continues, while the while loop continues, so long as the sum is not equal to 0. But if the sum is equal to 0, it stops. If the sum equals to 0, no, the sum divided by n. If the sum divided by n equals to 0, this while loop stops. But while the sum on division by n is not, the remainder is not equal to 0, the loop continues. And when the loop continues, it means you'll increment k by 1 and then also increment the sum by a. So you do that until you find k. And then there is a main function. The main function, again, I already explained what it does. You've given it n, so it knows that it will be dealing with 0 up to n minus 1. So it will ask for the order of 0, ask for the order of 2, ask for the order of 1, ask for the order of 3, all the way up to the order of n minus 1. And then the find order function will be doing that. And while once this one asks, the find order function does, and then gives the result, and this prints. Now, so that is how you to do the code for the additive group. And now I want the code for the multiplicative group. And so I begin by showing you the code for the multiplicative group. And then I explain how it works. This is a bit longer bit, is a longer bit than the other one. You know, this one, the way I designed it is I wanted it to, first of all, I've given it all the elements. First of all, it must find out which elements belong to this group. By finding out which elements are relatively prime. And so that one it does by finding the GCD. If the GCD is 1, it knows that element is relatively prime and therefore belongs to the group. If it belongs to the group, this one takes over and then finds the order of that element. But if it does not belong to the group, then it means it's not relatively prime. And therefore it has no order. It has no order because it does not belong to the group in the first place. And so there's the main function here that will then be printing the results. So this one has 3 functions. One function is to determine which elements belong to the group and which ones do not. And that is the GCD function, by using the extended Euclidean algorithm. And then there's this find order function. And then there's the main function. Now let's, I've input which elements? I've input 23. My element, yes, my element is 23. Now, as I've also put a maximum number of elements I wanted to print up to number 23, for instance. I wanted to consider 1 up to 23. That's what this means, maximum element. So you tell it where you want to stop. But if you wanted to consider all the elements n, consider from 0 to that is okay. You can also reduce this number to what you want. You may want to find the order up to element 16. And so you just tell it. So let's try to run this and see what the result is. So I wanted to give me all the order of elements in Z23. You can see the result at the bottom.
Yes.
So for instance, yes, for instance, it says the order of 1 would be 1. That means 1 raised to 1 gives you the identity, which is 1. The order of 2 would be that. The order of 3 would be that. Lucky enough, all these elements were relatively prime to 23. And it tells you element 23 is not in this group. So it's not relatively. So I told it to print up to 23. But then it tells me 23 is not a member of this group. So it can tell you what are members of this group and the ones which are not. So let's try 22 and see. So it will eliminate several elements here. Those which are not relatively prime to that, it must be eliminate them. So because they'll not have orders. Okay, it has already done that. It's telling us the order of 1 is 1, but element 2 is not a member of the group. So it's not relatively, it's not co-prime with the 22. That means it's not a member of this group and therefore has no order. What about element 3? Has order of 5. Element 4, you can see also it's not co-prime, it's not relatively prime to 22 because the GCD of 4 and 22 is not 1. The GCD is not 1, so it's not a member. So that is what I wanted. So what is doing this is the GCD function. The GCD function is giving us the GCD. And once the GCD is 1, we can tell that that element has the order. We can find its order. When the GCD is not 1, then that element is not co-prime. And therefore, it has no order, and so on. So that is what this one is doing. Of course, as I said, you can also customize this code so that just gives you the order of the element you want. Just gives you, if you want the order of 10, just give it 10 and 22, which is the mod. Then it gives you the order of 10. But I wanted to give me the order of every element. And of course, I also wanted to tell me what elements are members of this group. So you can see 10 is not a member of this group. 11 is not a member of this group. 12 is not a member of this group because they are not co-prime to 22. So it cannot find their orders. Okay, so I just want to explain how it works. Of course, you can give it even a very big value, but I don't want to do that. I don't want to do that because it will take time. But I've told you the function of this maximum element. You're telling it where you want it to consider up to. For instance, let it consider it up to 6. So let's try and run this and see that it will consider up to 6. Yes, so it considers element 1, 2, 3, 4, 5, and 6 only. So that is, you can set a maximum of where you want it to consider, and it does that. So that is the importance of this. This is the function of that. So it gives you where you want it to reach. Now, so the GCD function, we had talked about it earlier several times, but of course, I'll still repeat how it works. I'll still repeat, and you see, you give it 2 elements and B, and it wants to calculate X and Y so that the GCD is written, the GCD of and B is written in terms of X and Y. That is what it's looking for. So first of all, it gets the GCD and then finds the values X and Y, those factors. And look at what it does. It lets X to be A And it says this will be mutable, changing with the time. Then it lets y to be b. Then again, this will be mutable, changing with the time. Then there's a while loop, It says, while y is not equal to 0, while y is not equal to 0, proceed inside here. While y is not equal to 0, perform what is inside. So let y be temporary. Let y be temporary. You store it as a temp. And then what becomes of y? Y will now be the remainder of x on division by y. The remainder of x on division by y. That's how we write it. So y becomes the remainder of x on division by y. What about x? X becomes the temp. What was temporary becomes x. And I had shown this example earlier. That's how we find the GCD of two numbers. As we find the GCD of two numbers, I just want to again show it just for to assist those who are not present that time. How this code will be finding the GCD of two numbers. And I can see time is running. I just want to show you how to be. Now, supposing I have 8 and 3, and I want to find the GCD of 8 and 3. Now, so I want my A to be 8 and my B to be 3. So it says let x be A. Let x be A. And let y be B. Let y be B. So then what happens? This one be mutable. So the next step, what is y? Is y equal to 0? Y is not equal to 0. We are at this loop. While y is not equal to 0, proceed. So y is not equal to 0. Y is not equal to 0. So therefore, we proceed. And how do we proceed? We let y be temporary. Let temp be 3. And then what about y? Y becomes the remainder of x on division by y. The remainder of x on division by y. X is 8. Y is that. The remainder of x on division by y is 2. What about x? X becomes the temp. What was temporal? What was temporal was 3. So x becomes 3. Now, again, we ask ourselves, we come back here, the while loop, you can see that y is not 0. Y is not 0. So we proceed inside again. We just remain inside until y becomes 0. We remain inside until y becomes 0. So since y is not 0, the next step again is here. Let y be temporary. So let temp be y, and y in this case is now 2. And then let, don't let, get y. What is y? Y is the remainder of x on division by y. The remainder of x is 3, and y is 2. So the remainder of x on division by y is 1. Let me write it here. So y is now 1. What about x? X becomes what was temporary, which is 2. Again, y is not equal to 0, so we proceed. We repeat the steps. Y is not equal to 0, so let temp be y, which is 1. So what is y? Y is the remainder of x on division by y. The remainder of x on division by y is 0. And what about x? X becomes what was temporal. And then when y becomes 0, the GCD is the x. So that means the GCD, therefore, of 3 and 8 is therefore x. Our x is 1. The GCD is x. So that is how it does to find the GCD. That's how it does to find the GCD. And now, what about how does it do to get prime numbers? So this one, no, not the orders, to find the orders. So this one, of course, once it finds the GCD is 1, for instance, 3 and 8 is 1, it means this element 3 is a member of the group. And so it comes to the find order. Find order, it comes here. This one will be find the order. And of course, what it does, our 3 is input, our n, which is 8, is input. And then it says, this is a loop. Of course, it says, if the GCD is not equal to 1, if the GCD of A and N is not equal to 1, then it will print none. It will print none. That means that this element has no order. Has no order. Now, if this is not the case, then we come here, where the GCD is 1. Where the GCD is 1, it comes here. Then we repeat the process we did earlier. We let K be mutable and make it 1 initially. And then this time, the other one was sum, but this one is now power. We let the power, because what we want A raised to K. So we want this to be 1. So we began by letting K be 1 initially. And then we also let initially the power. We let this power K, the power here. Yes, we let the power to be A. We let the power to be A. This is the power. Now, let me use a different number here. Let me use a different number, first of all. So this power is what we are calling it. Initially, it will be A. But now we are looking for, what is that power that will give us this? So this power that will give us this is what we call K. So initially, we make it to be 1. This power, we shall call it K, but we initially make it 1. Okay? And then, while the power is not equal to 1, while the power is not equal to 1, we perform what is inside. While the power is not equal to 1, we perform what is inside. And what is inside? What is inside is to get the new power, and the new power we get it by multiplying the old power by A, then divide the result by N, and then write the remainder. Write the remainder. And then the other thing is, then we, after doing this, we let new K to be the original K, which was 1 plus 1. So K now goes to 2. K goes to 2. And repeat this process until the power is 1. Until the power is 1. So we repeat that process. So let me just show you one thing. For instance, suppose we let K to be 1. And let me talk of, for instance, we have 3 and K and 8. And we want to find the order of 3. Want to find the order of 3. So we let K be 1. Let K be 1. And then let the power, let the power be A, which is 3. And then the new power now becomes the power which is 3 times A. In our case, A is again 3. This result divided by 8. And of course, what we're interested in is the remainder. What you're interested in is the remainder. Look at this. While the power is not equal to 1, you continue doing what is inside. But we've already found that our power is 1. So when our power is 1, we now exit. We now exit and write the order. So the order becomes some k. The order becomes some k. So initially k was 1, then after multiplying that, then k becomes 2. K becomes 2 after multiplying that. K is our 2. So you look at that, of course, that explanation I've put it here. There's an explanation, I've put it down here. You look at it later so that you understand it. Thank you. I wish to stop there.
Thank you, Dr. Sakwa. Thank you, everyone, for appearing today. I think today's class was really interesting, and we followed through all the way. So thank you, Dr. Sakwa. I'll confirm tomorrow's class if there's no on-chain Safari. But yes, I think we should continue with tomorrow's class as normal. Because last time they brought it to 5 p.m. and then we missed the session. So see you all tomorrow.
Thank you.